My name is Christoph Strobl. I work for Pivotal as an engineer in the Spring Data team, basically focusing on the store abstractions for MongoDB, Redis, Solr, the key value stuff. But I also do changes on the JPA module as well as the newly introduced key value one. And we're gonna talk today about a very specific group of Spring Data modules, namely those that you can use for search, full text search, and that's what basically makes up the agenda. So if we take a quick look at the history of search within the Java ecosystem, it basically turned out to have started in 1999 when Lucene was initially released. So Lucene is up till today the core technology for most search engines that are out there for Java. And so basically it contains all the stuff you need to analyze your text, to categorize it, to store it in the proper way. And most of the more modern search technologies are built on it. So basically 2004, the Apache Solr was released. So this added basically a server component around the Lucene search technology. So up till that, from that time on, we were basically able to access search via a dedicated component within our infrastructure. We were able to talk to the search engine via a REST-like interface over HTTP. We had various input and output formats. So Solr was capable of dealing with XML, CSV, and all that stuff. And it had a query API that you could use via an HTTP request. So this was pretty awesome. And there were several features that haven't been covered in Lucene so far, like faceting, we'll come to that later, that were only implemented in Solr. So it took quite some time till those two projects basically joined forces and merged, more or less. And that was the time that, for example, faceting got merged into the Lucene core capabilities. So Solr has been around for over 10 years by now, and in 2010, there was some competition on the search server market for Java with the release of Elasticsearch. And this was a kind of good thing because it brought competition, and Elasticsearch solved some of the problems that hadn't been addressed so far by Solr itself. So in 2010, what you had was basically one search server if you were using Solr, and no cluster. So if your server was down, you had to somehow deal with it on your own, and you weren't able to cluster it or shard data. And that was something Elasticsearch came up with. So it was pretty easy to spin up a cluster of search servers that were connected to each other and did the sharding for you and the automatic failover, which is pretty awesome. So the Solr community had to do something about it, and this is nice to see that by now the clustering capabilities, though differently implemented, are part of Solr as well. So you see the competition brought something for us all, for the community. And since we have a dedicated Spring Data MongoDB module, and MongoDB released with its 2.6 version search integration within their store, we're going to have a look at that as well. Though I must admit, the search capabilities within MongoDB are A, not based on Lucene, so they did their own thing, and B, MongoDB is no search server by definition. So the first two, Solr and Elasticsearch, are fully fledged search servers with all the capabilities you will want to have for building your applications, while MongoDB just offers full text search as part of its database. So there's a distinction in there, so please don't mix up things and go out of this session and say, hey, MongoDB is our full text search engine. That's not the case, but you have the capabilities in there. Good. So in today's session, as I already said, we're not going to cover internals of Lucene or dig too deep into that, but we'll have a look at how we can do full text search with MongoDB, with Apache Solr and Elasticsearch, and how we can use the Spring Data abstractions on top of those technologies and what it means for us when we use it, so the potential pitfalls and all that stuff. But before we start, what is this thing with search basically all about? I mean, in my opinion, search is a pretty simple requirement. I mean, I want to find my data quick and easy, and I have seen applications that failed, not because they were poorly implemented or badly tested or had bugs or missing features, but simply because they were unusable because users weren't able to find their data. So there's a kind of funny story when I went to a local bookstore a few weeks ago in my hometown, and I was asking for a specific book, and I was telling them the author and the title. And the guy at the counter basically told me, oh wait, let me just quickly open Google and search it in there and then copy the ISBN, so basically the book number, into their very own system, because this is faster than searching within their own system. So, well, in my opinion, that can't be the case. And if you have, let's say, sensible data, so if you have a call center application dealing with thousands of customer numbers, first names, last names, sensitive data, you cannot just go on to Google and search the person in there and then copy some internal ID into your system. So you get to do something about it without potentially killing the database by executing what have you SQL statement against it, basically doing a full table scan on, or even worse, multiple full table scans. So it's a simple requirement. I want to find my data. I want to find it in a human readable way. That's also very important. I don't want to know about some expression language I have to understand before I can even enter my search term. I want to have it like Google has it. That's the requirement. I want to type in something I can easily understand. So it's a pretty simple requirement, in my opinion. But the thing with simple requirements is that this can be implemented pretty easily. But the thing is, people make mistakes. And I also want to work my search if the user makes mistakes. So this is something a search engine should be capable of. So if I have a typo in my search query, I still want to have it to do the right thing for me. I want to find the documents though I made a mistake. So I'm sorry. A pretty simple requirement can turn out into a really complex solution. So this is basically the algorithm for the Levenshtein distance that is used to calculate the distance between words based on the distance of each character to the other. Thank God there's much more smarter people than me who provided us with some kind of abstraction. So this is basically what the Elasticsearch representation of the Levenshtein distance algorithm in a developer readable way. So you need to learn some syntax, and then you can go on and make use of the work someone did for us, thankfully. Great. Having that said, I want to quote Neil Ford a little bit, because this is more or less the model for this session. You need to understand one level of abstraction beneath the one which you're working on. So basically we have this Solr, Elasticsearch, MongoDB abstraction around those complex algorithms within the database or data store that do the work for us. Then we got the driver for that specific store as another level of abstraction that mainly offers really direct capabilities. So I have to know about the query language in there and all that stuff. And on top of that, we got the Spring Data repository template and repository abstraction. So there is quite a lot of layers in between what's happening in the store actually and what the API you get exposed to. And so we'll try to have a look at the stack in between so you understand what happens in the specific parts of those components. Okay, anyone who doesn't know what Spring Data is all about or hasn't used it so far? Oh, yeah, a few hands, okay. I'll go over that real quick. So this is an introduction session. So Spring Data is basically composed of several modules. So we have the core set of modules, which is commons, which holds common types that we use in the different store implementations, like a page that holds contents and tells you about, is there a next page, a previous page, and all that stuff. We got implementations for JPA with the several JPA providers like Hibernate, Eclipse Link, and all that stuff. We got support for MongoDB with both driver versions 2.12.3, I guess was the latest, and the 3.0 version line. We got Neo4j, we got Solr, Gemfire. The odd one out is REST, because it's not really a store abstraction, but more how to expose a repository into HTTP resources. We got Redis and the key value module. There's also a lot of community modules and work going on there, because there is Couchbase, there is the Elasticsearch module I'm going to present you today, which is actually not maintained by us, but by the community itself. So there's a bunch of guys in London who liked Elasticsearch a lot and who liked the idea of Spring Data a lot, so that they basically sat there and implemented that stuff. And it's really cool to see all those community projects evolve and grow. And there's one for Cassandra as well. And as I said, there are many community projects. Some are incubating currently. There's one for Crate, there's Aerospike. Those guys did a lot of work recently. And there's even one pull request open for Spring Data repository abstraction for Hazelcast, because that store also offers its own query language, so it's kind of natural fit. But we're gonna have a look at those three. And as you saw, there are many modules within the Spring Data releases, and we basically try to group those releases together so that you don't have to deal with the different versions of the modules, because all of those evolve on their own pace, and we don't force them to upgrade to a common version line. So basically, there's, I think Elasticsearch is 1.3 currently, while Solr is 1.6, and the JPA is 1.9. I hope I remembered that correctly. But we try to group them together and do some semantic versioning. And we basically name our releases after famous persons in our industry. So we started in 2013 with Aurora, Babbage, Cott, Dijkstra, Evans. The Fowler release in 2015, and Gosling is currently the latest release. And the next one will be named after Grace Hopper and is about to go GA somewhere in November if everything works out as it's planned. And to make it really easy for you to pick up the versions, and so that you don't have to remember all of those versions, we offer you something that's called the release BOM. It's basically a POM file holding all those all version numbers as properties, so you can later on override it. And all you have to basically do is enter the artifact ID, which is Spring Data release train, and then add the Gosling release or SR1 or the Fowler release, the one you choose. And then go on and add that stuff to your dependency management section in Maven. And then you can basically go on and, oops, there you go, and declare your dependencies without having to worry about explicitly defining the version for, let's say, Spring Data REST Web MVC. and MongoDB, because those versions that work together are already defined in the release POM. So let's have a quick look at how Spring Data actually works. So we have several layers of abstraction. So very low layer is the template abstraction, as you may know from the JDBC template or the JMS template or what have you in Spring Framework. So it's pretty easy to find your way around if you have used one of the others already. And this gives you basically access to the lower level APIs of the specific stores. So this is something we try to do with Spring Data, is not to shield you from using native store APIs. So you can use them if you want to, but we try to offer you higher abstractions, but you still can use the lower ones. So this is basically setting the profiling level for a MongoDB database to debug mode, so log everything. On top of those low-level templates, we got the repository implementation, which is basically that part we have that does all the proxying for you to get an actual store-specific Spring Data repository implementation. So that this is the part that lets you define just an interface, so that you don't have to write your data access code all over again. So we offer you basically the abstractions for CRUD repository, paging and sorting repository, and with that you basically get all the stuff you naturally expect from there. So you get save operations, you gotta find all operations, you can find something by an ID, and of course you can delete all the stuff again. So there's delete all as well, but I wouldn't use that too frequently, actually. And the cool part is the last part I'm showing you in this really short Spring Data introduction. There's much more to learn and to see, but there's dedicated talks out there in the web you can watch or see, or you just step by later on and we'll have a chat. So basically what we offer you as well is the derived finder method. So what we do here is we analyze at startup time the method names you put into your repository, analyze the return types, and figure out for you what the query should look like that we are going to execute later on. So find by title, returning a list will basically read all documents from a MongoDB that match a given title, or you can use the page abstraction. So we provide you with out-of-the-box pagination, so you can basically use the pageable parameter to define, hey, I want to get page 1 with size 10, and it gives you the correct result in return as part of the page and tells you, hey, there is the next one, and this is, by the way, the pageable to use to get the next page. You also can use delete by author, which will create a delete query. Or recently we added support for streaming. Basically, this is available for JPA and MongoDB, where we wrap cursors so that you can make use of the Stream API, the Java 8 Stream API. Good. So we're done with our really fast introduction to Spring Data. So let's get dirty with some search technology. And in order to do that, as I'm going to be use a few terms later on, I think we should have a look at least the following terms. This is, in first place, what is a schema? What does a schema mean in terms of search? I mean, schema is more or less the same stuff as you're used to from relational databases. So it basically tells you in which format a given data type is stored and what to apply. But there is a little bit more when you use it with search, but for now, that will do. Then we'll have a look at a little bit of text analysis. What does it mean? How can you use it? What does it look like? Are there pitfalls? What should I better not do? We'll have a look at what scoring and boosting is. as those are terms that will, and a short look at query versus filter query. Okay, so let me just quickly step out of here and fire up an Elasticsearch instance. Okay, this may take a second or so. So I'm using a single node Elasticsearch for this demo, and I wanted to show you just a little bit of the Elasticsearch configuration. So what we basically have here is the Elasticsearch YAML that's in the configuration directory of your Elasticsearch distribution. And what I did here is basically define a cluster name, because Elasticsearch has the capability to basically find cluster nodes by itself. So, and by the cluster name. So if you don't configure it and fire up several nodes on your local machine, they will find each other or even reach out on the network, which is kind of a bad thing on a conference, because it potentially may join some other cluster that might be around here. So I gave it a dedicated name and hope that no one else has it. And in order to make sure that really no one interferes currently, I also use this little friend down here, which is called, can you actually read it? I'll zoom in a little bit, which is called network host. So this little friend basically limits in and outgoing connections to my local machine, just to make sure that no one interferes. And this is also helpful if you're working in a company and don't want your local Elasticsearch connect with all the others within the company network. And there's one more option that might sometimes be helpful, and that was the cluster, the node name. So by default, Elasticsearch, when it starts up, picks a random Marvel comic character name. They have some connection in there. I don't know actually what it is about, but there seem to be 1,600 Marvel comic characters, and it just picks a random name for the instance you have, which can be nice in some way, because it's kind of funny to see all the names you potentially know. But it's hard to figure out in logs which node had this name at that time belonged to before it crashed, because it potentially has another name when it starts up. So I would recommend to set this, but for now I have, let me see, oh, it's already started. So let's have a look at the dashboard that you can basically install as a plugin. So I guess most of you noticed this is Kibana, and I installed it as a plugin into my Elasticsearch distribution. And what this does is it gives me a general overview about my cluster. So I can basically see here that it's a cluster of one, which is normally not a good thing, because it even shows that all the stuff is red here because there are no replicas assigned. So if the node dies, all my search is gone. I also got some information about CPU usage and all that stuff. I'll make it a little bit bigger for you. Oh yeah, I don't know that one. That would be the automatic comic character Marvel node name I have for this machine. But what the Marvel plugin also comes with is this really nice and handy tool that's called Marvel Sense. It's a JavaScript page that offers you auto-completion based on the Elasticsearch API, so you can basically get index information from in there, and you have auto-completion on put. It detects the indexes you have in there, and it helps you writing your queries and trying out Elasticsearch and playing around. You can also use it to do some analytics and what have you. So it's really, really nice plugin. It's free for development mode. You have to pay if you want to use it in production or somewhat. But yeah, so much on that. So what I actually did is I preloaded Elasticsearch. Let me just reinitialize that. So I preloaded the Elasticsearch index, which is currently the S2GX index, with some sessions from the data and integration track. So basically I added the the talk Thomas and Ollie gave right after breakfast, so the What's New in Spring Data talk at 8:30 to the track data and integration. And what you already see here is that it takes a JSON document. So that's a really nice thing about Elasticsearch, that I can use JSON documents to push to the index. And what Elasticsearch then does, it analyzes the data I pushed and tries to figure out the schema. So basically, it analyzes the data I give it and auto-detects more or less that the title will be or might be a string field. It will also see, hey, there is a field called date that potentially, or more sure, will be a date having a time. And the track might be a string, can be something else, but it will be a string. And what Elasticsearch then does is it creates a schema for you. And this is important because all those search server implementations based on Lucene require you to have a schema, though most of them. I mean, Elasticsearch claims to be more or less schema-less, so does Solr as well. But there is always a schema behind that stuff. So there is a schema in the search server itself. And you can have a look at the schema. And as we expected, there's basically mappings. And within the sessions, there are properties. And as you can see, there is a date of type date. So Elasticsearch recognized it as a date with a explicit pattern. So the time is optional in this case. It recognized the title as a string and the track as well as a string. This is really nice and cool if you're working with that, but as you can imagine, and since there is a dedicated schema in there, I could just go on and try to do that one. Error document. And put some invalid field in there because to someone's mind came it that the date can look like this. And when I try to edit, it basically returns me an error telling me that I cannot add this document to my index because the types don't match. So in this case, it's very obvious that it won't work, but assume you got numbers in there. And the first time you pass in a document, it might be an integer value. And this works fine for a couple of times, and then you suddenly start passing on longs. So now you get a problem, because the schema tells it's an integer. You passed in a long, you get an error. And what you have to do then is a schema migration. So you basically have to reindex all that stuff, because you cannot just change field types, as Lucene won't let you do that. So you really have to be careful. I mean, it's pretty easy to push on documents, but you have to think about what representation the documents will have within your store, and especially in Elasticsearch and Lucene. I mean, MongoDB is a different beast. MongoDB is completely schema-less. In MongoDB, you could do this, though the search will be limited depending on the type you enter for your search. But in MongoDB, it's possible. It's not based on Lucene. It's a different beast. Okay, so that was a real short look at what a schema is, what it does, what it's used for. There's a little bit more in the schema, because you can also add information on how data is treated. So if you store a document, you can basically define how the string, let's say, the string of certain fields is treated, if it's split or taken as a whole, or if numbers are eliminated, if it's lowercase, what have you. So Elasticsearch applies a couple of those by default, but to give you a real impression is basically to do some analyzation on this particular string, which is Spring 1 2GX 2015 in Washington, D.C. And when I try to analyze that, you can see that there is a bunch of tokens returned. A token has always an offset, a type which is alphanumeric. You can see for 2015 it detects that this is a number. There is no it's not alphanumeric, so it can be treated differently. Yeah, that's basically it. So you know every token gets a position and the token value, it has an offset, and so on and so forth. Oops. So there is a bunch of different tokenizers. So I could just I could just remove the numeric part by using a different tokenizer. So if I'm not interested in my search in any numeric value, for whatever reason, I could just go on and use a letter tokenizer, which by default removes the 2015 from the string in there, and even the 2 from the 2GX part token. Okay, that's to the tokenizers. Additional to the tokenizers, I can apply filters to the tokens extracted by the tokenizer. So what does that mean? Basically, if you don't define any filters, you would have to have exact matches. Basically, for Spring 1, it would be halved with capital S and capital O, but for search, that's not always the best thing to do. So you basically want to do a lower it within your search index to A, take less place, and B, to be easier searchable, because the user doesn't have to care about the original value and camel casing and what have you. And what I could do as well is I could filter duplicates. So if I have Spring 1 to GX, Washington DC in Washington, well, I could, when I now go on in lowercase and unique that, you will see that Washington now only shows up at its first, when it's first encountered. So as always, there's a little pitfall, because the order of filters matters quite a lot. So when I mess it up and put the unique filter before the lowercase filter, it won't be able to eliminate the terms, but still lowercase them all. So what happens if I do it that way? You can see there's Washington at position 4 and at position 7, so both lowercased, and that doesn't make too much sense. So you have to be aware of that when you're dealing with schemas or try to add filters to the implementation. So the order really matters, and whoa, that's not what I wanted to have. Thank you. Okay. Good. So let's do a basic search. Real quick one. Find all documents. Don't care about anything. Just to tell you a little bit about scoring. So what I did now is I executed a search that gave me all documents within my index, which is basically the sessions out there. And what I wanted to show you is that Elasticsearch returns you the number of total hits. So you automatically know how many documents are in there, which is a perfect match for Spring Data page abstraction, because we always tell you how many documents match your search. It tells you the maximum score that was encountered and all the documents that match your search. And there's this one field, which is the score field. So score basically tells you the relevance of a particular document related to the search terms you entered. I didn't enter any search terms, so it's all documents are equally relevant with 100%, because I always wanted them. So as you can see, there's score there and score there. One side note, Elasticsearch always returns you the original data structure, the original JSON structure within the source element of the JSON returned. Okay, now let's have a look at, let's say, another search. And as you can see, I looked for all I did a full text search on data, so it basically returns me all the documents that have data in it. And those are now ordered by the scoring, by relevance. This is the default behavior of Solr and Elasticsearch. MongoDB is, in this case, a different beast as well, because it will use a natural order, while Elasticsearch and Solr always return you a scored order if you don't define it differently. So the most relevant document will be always the first hit, and yeah, relevance is calculated by word position in the fields and how often it's there, and there's a really complex algorithm how it's done. But you can have influence on score. So if I basically try to query for multiple fields with boot and data and the title of track, you can see the score changed because there are multiple search terms, and I restricted it to fields. And the score values now look differently. And this is something very useful because you can give your users information in how potentially relevant the result you present them is. But you can also influence the score a little bit. So this is something we call boosting, because I want to have a hit within the field title to weigh much more than potentially within the categories or within the tracks, because I'm not really interested in those. I just want to find these sessions that have boot and data within the title. And what I do here is query time boosting. So I tell the search server to treat a search hit within a certain field differently so that it weighs more, which is expressed by, I don't know the English word for it. It's circumflex times 2, I don't know, power 2. Yeah, okay, basically that's the syntax to do so. And if we have a look at the currently Spring Data REST meets hypermedia and security is rated top. Let's see if that, no, it still is rated top, but it has a different weight in there. While this session moved up from below. Yeah, exactly. So the first hit didn't change because it's the top hit, but the second one, you see the order changed depending on what you defined within your query, which is kind of nice because you can do it when you search actually, and you can also define it prior within the schema, so you could define it there so that the user doesn't have to care, but you also can do it at query time, which is really, really nice. Okay, let's move back. There's one thing I didn't tell you already about, and that's the difference between a query and a filter query. So we heard about scoring before. Is it just gone? Hello? Let me try again. Hello? Oh, I crushed the beamer. I'm sorry for that. I don't know what just, oh, it seems to come back again. Oh, wow. Okay, thumbs up. Yeah. Okay, back. I wanted to tell you about query versus filter query. So queries basically have influence on scores. So what you search for, well, yeah, exactly. So filter queries don't influence score. So you basically can define criteria to eliminate documents from your search without having influence on the scoring. So the order will remain as if you hadn't defined a filter query. So yes, thank you. Exactly. So let's jump right into it with MongoDB and see what capabilities we have in there, how we can build a search index, and how to use the MongoDB full text search in there. So for this sample, I'd like to show you something that's basically, I hope you all know this site. This is our very own website with our blog. And what we have here is we integrated full text search in there. That's actually backed by Elasticsearch behind the scenes. And what I want to do is I want to search for a specific Gosling, a specific search term, and as expected, I find the latest Spring Data release train and all that stuff. What I wanted to show you is basically that stuff around here, which is something called facets. So facets are the part used for guided navigation. So it basically tells you that there are documents that have a certain type, because every blog post is either a blog, every content in there is either a blog post or a guide or what have you. And blogs are categorized in engineering, news, and events. So every blog post has basically is assigned to a category. And what faceting does, it tells you how many documents matching your criteria actually show up in one of those categories. So you can basically guide your user to certain categories, or like Amazon does, it tells you, hey, there's 15 hits in fantasy books and 2 in others and what have you. So that the user can basically drill down and get more concrete in what he's looking for. So this is really nice. And what we also have here, I hope the Beamer resolution allows this, is highlighting. So my search term, yeah, I guess it's readable, is highlighted in some way. So in this case, it's bold and it has a different background color. So those are nice features that search can provide you with. Although I must admit, those highlighting and faceting capabilities are a part of fully fledged search servers like Elasticsearch and Solr. There are plans for faceting for MongoDB as far as I read in their Jira, but that hasn't been implemented so far. But for the major stuff, so if you don't depend on having guided navigation via facets or highlighting and that stuff, MongoDB can do a pretty good job. And so let's build a blog post system having full text search. Let me just fire up MongoDB. And use test. So what do we first need to define? Is it? Can you guys read that from the back? Is it okay? Or let me just move it. Nah. Oh, won't go back. Okay. Let's move it up a little bit. So I hope that's better. What we first need to do is we have to define a special index in MongoDB, and we can do so by calling an ensure index, giving it all the properties I want to have. I want to have full text search able, and to do so I have to add the text keyword basically as type, and the part you can see down here is basically influencing the score of a document when it's searched. So as in the example before, I want to weigh a search hit in title way more than one in content. And this is basically the way you have to, the only way at the moment you can influence scoring with MongoDB. So this is index time boosting, and you have to think about it before you actually create your index. Of course, it's pretty easy in MongoDB to just drop the index and recreate it and it gets done for you, but you have to think about it. Otherwise, your search results might be potentially a little bit lousy. Okay, so let's add this index in there, and then just insert some random JSON document. As you see, I have the title in here and the content, and I just add it, and then I go on and use MongoDB's syntax for text search, which is basically, I added a query with $text indicating I want to do a full text search, and then I give it the search term indicated by $search, and I search for any document that has in title, content, or category the string in, and I want to print it. And yeah, well, that doesn't return any results. So why is this? This is because MongoDB comes with built-in stemmers, tokenizers, stop words, what have you, for 16 or so languages. I hope I didn't say something wrong in here, but it should be 16 languages. And what those tokenizers and stemmers do for you is basically, in order to keep the search index small and fast, they eliminate common words. And in is a very, very common phrase. So basically, when MongoDB sees the document up here, it recognizes, hey, this is a stop word. Forget about it, I don't need it. And so you won't be able to search for it. That's something you should be aware of when you're using MongoDB. So your search terms should, the thing you want to search for should be in some shape that is MongoDB is okay with, because you are not able to customize how it behaves, because it's just built in there and ready for you to use, but you cannot change it. But it works pretty well if I just go on and search for, let's say, Washington, then okay. You see the content in Washington was basically, the term was contained in the content field and just returned it to me, and everything was fine. Okay, so let's just drop the index again, and let's see how we can do this with Spring Data. Okay, using Spring Data, we have basically the very same structure. We have a blog post that has an ID, a title, a content, maybe assigned to a category, and what you see here is basically the score, because I'm interested in the score. I'm interested in how good my search results are. So I added the score field in here to pick up the value. And what this little friend here does, it tells Spring Data to ignore the property for writing. Yeah, question? Oh, sure. Yeah, sorry. Okay, this little friend tells the Spring Data abstraction to just ignore it for writing, but if it's there in the result, it just reads the value back into your domain type. Okay, let's go on and do some simple search. So as you saw before, we can create the index manually on the console, and with Spring Data, you basically have something called a text index definition with a builder. So we basically define, hey, on the field title, I want to have a weight of 3, on the content field 2, the default is 1 for the categories field. Then I create the index definition and tell the index operations for the blog post type to just create the index for me. Pretty simple. And then I can go on and, just define a text criteria for a default language, which is in MongoDB basically English, but I can use any of the other 16 one. Matching any search term I enter in here, which may be release, because I just downloaded a sample of our blog to show up in here to have a concise result, and then basically execute that stuff using the Mongo operations call find with the criteria. I can basically chain other criteria to the text search one as long as I don't use a special index such as a geospatial search. I can use other terms to combine it. So I could basically also say, and the document must have category, release, what have you. Okay, and that basically executes the search for me. And what you see down here is the result, and notable is that the score field though I have it within my domain type, is currently null. This is because MongoDB doesn't by default return you the score field, because it takes some time and blows up the result size and what have you. So you have to explicitly tell MongoDB to give it to you. And you can do this by defining a text query given this very same criteria we had before. And you have to define the field of the score field, and then you can basically also sort by this field. Otherwise, you wouldn't be able to sort via the score. MongoDB returns natural order, as you can see down here. This is just I order the way they're within the store, and then you can basically go on and use the score to order your results. And when I do that, let me just execute it. You can see that the score field is now there for you, so so it got returned to you, as well as that the order of the results is different, because we now order by score. But there wouldn't be Spring Data if we weren't there to try to make it as easy for you to use this technology as we can. So what we provide you additionally with is something called the text score annotation, which is basically, which has the read-only annotation as its meta annotation, so it's basically a read-only field. But when we detect a property that has this annotation within your domain type and you're using MongoDB, we assume that you're interested in this score. So we add that additional part to the query that you otherwise would have to type. And so that the score always gets returned to you. And what we also have is we have the automatic index creation for you ready. So you can basically add the text indexed annotation in there, give it a weight like we did there before. Let me just copy that. Whoop. Let's call this 2, and that one has no weight because the default is 1, but it should be indexed. So this is pretty much all you need to do to get rid of what I showed you here about this little stuff. And what I can now do is basically, I have my domain type defined. I added those annotations, and I can do basically the same search, just using repository abstraction without having to interact with any of the templating stuff or the lower level APIs. So it's pretty easy. All you have to do is to pass in a text criteria, or use the text criteria as part of some other criteria. We'll detect that, and then just execute the full text search query. That's pretty easy. Yeah, you can also combine it with non-matching and what have you, all the stuff that MongoDB basically offers you. Okay, time moves on. I have to hurry up a little bit. Great. So I think we're basically done with the MongoDB abstraction. I showed you that there are stemmers and stop words, that the score isn't returned, that you have to explicitly have it to sort. We did the index creation and the automatic index creation. We did the querying and the scoring. Yes, thank you. Oh yeah, there's one thing I wanted to mention as well. You also can make use of the scoring within the derived queries. So you can basically use the natural Spring Data or the by clause within your method declaration, and it will just work as you expect it to do. So this is pretty neat. Exactly. Okay, questions so far to MongoDB? Otherwise, I'll move on to yeah, question.
Does the Spring Data Elasticsearch use the REST API or the transport API in Elasticsearch?
Boo.
Transport only?
I don't actually know, because it's one of the community modules. I can check with later on. We can have a check. I'm sorry, I don't actually know that. Okay. So moving on to Spring Data Solr. And as I said before, there is no Lucene-based search server that's really schemaless. So what you have in Solr as well is something called a schema, and apparently it's an XML document. Within that XML document, you have the fields defined. So basically, there is an ID that's of type string, and now comes the interesting part. It's indexed. You have to set the indexed value to true in order to have it searchable. If it's false, you won't be able to query for it. It would give you an error that there is no such field and doesn't know anything about it, and that's all. And the next attribute is stored. So what does stored mean? Stored means this property is there to be returned to you as part of your search result within the document. Okay, it's required and multi-valued. That's nothing really special. But if you basically have a field that's not stored, it can be potentially used for searching. So you have, as in Elasticsearch, special fields fulfilling a dedicated purpose. So if you have a title field, or let's say a name field, then you store the name as it is normally within your index. It's typically indexed and stored, which means it's part of the result. But for searching, you want to have probably a lowercase field in there, so that the user doesn't have to worry about case in his search terms. So you have to add an additional field that might be of type lowercase, which then is not stored, because who is interested in the lowercase result? Pretty much no one, but it's useful to have it in there because you need to query for it. Okay, and here you can basically see a field type definition. As we saw before, there's this field called name that has the type text general. And behind that field type definition, there's basically the information how that field should be treated within the search server. So basically it gets tokenized by the standard tokenizer factory, which just takes the string as it is, not applying any tokenization. You could use letter tokenizer and what have you. There is a bunch of those listed up at the website. I pretty much explained what they do. And then it's a lowercase filter factory, which just lowers the string for indexing. So basically, all the values are written lowercase into the index. And you also can define a special treatment for queries. So when a query comes in, the string provided the query string is also tokenized, and stop words are limited, and all that stuff. So there's really a lot behind the type information that gives you. So you got several points to tweak your index in there and how your search behaves by just adjusting the field type definitions. But again, you have to be careful, because or think about what you want to do before you go into production with it. Because again, if you change stuff in there, this can probably result in the need to reindex the stuff. And reindexing, depending on the size of your index, can take several hours or days or really, really long. Okay, and what Solr also has is something called the managed schema mode, which is basically more or less the same as we have in Elasticsearch. So Solr takes the first document it sees for a collection and then tries to somehow guess the field types. And let me just spin up a Solr instance for you. So I'm using the example that comes with the Solr distribution. So there's basically a an example of a cloud setup within the distribution that you can use. It's pretty simple to start up, and then it just allows you to go to the Solr admin, which looks like this, and you can see on the Cloud tab that there is basically one index that's called Getting Started, since it's the example. It's started. There are 2 nodes actually available, and what I have down here is the index itself, and I can go on and query in there. And behind all that, there is the schema. So the schema is basically hidden in some file within the index itself. It's called managed schema in this case. And down in there, so there is a basic configuration in there. You can see that there are already field types contained, and there is a name field that has a type of text general, and there are dynamic fields in there, so you can basically define wildcards so that every field that ends with _I is treated as an integer. So there is a schema underneath, and it's in that particular file that gets updated. So if Solr sees a new field when you add a document, basically the field is added to this very file. Okay. So, and when I now want to search Solr, I can basically go on and take the field names in there and do some wildcard search, starting with all the documents are returned to me that start with a CAN, which is basically Canon, or there's a PowerShot and what have you. And what I wanted to show you is basically highlighting in there, as we saw it in the blog post example. So with Solr, you have to really know about the query string, so you have to learn the query language. And highlighting is one of those stuff which is represented by HL for highlight, but you have to know it. And then there is FL, which is basically the list of fields highlighting should be applied to. So it's not that really nice of a usage. So you can basically add a star, which is apply it on all fields and do the highlighting in there. And this is remarkable because here you see the response with the document, and those are 2 documents. And down here below, next to the actual search result, there is the highlighting result. So the highlighting is not actually done within the document you get in return, but next to it. That's the same for Elasticsearch. So you have to manually check which IDs down here match one of the documents up there to merge together the string in here, because there is that canon is defined, and here is in the name field it's highlighted. So it's not automatically included, and that is also reflected within the Spring Data Solr as well in the Spring Data Elasticsearch abstractions. There are highlight pages and faceting pages and all that stuff that pretty much give you access to the highlighting as it's returned from the store implementation. So we don't do the merging for you. You still have to do it manually because we don't want to interfere with what is natural to the store, and that's how they work. Okay, so getting back to the presentation. Okay, we saw the managed schema. One other thing that I wanted to mention is that for full text search, you need something like copy fields in Solr, which basically you define a set of fields that you want the values to be copied into another field. So normally you define an underscore text underscore what have you field, and then define a rule copy field source star, all the fields that are in a document, copy them into the destination text field. And then you can go on a query for the underscore text, what have you, and that's the way how full text search works in there. So, but what, sure. Let's have a look at a simple Solr query. You saw it in the API before. In Java, it looks a little bit different. So this is just a random method, find by name or description, given the name and the description, and we want to look it up in Solr. And what I need to do without the Spring Data abstraction is basically go on, take the query string, know the name, escape the input, because there could be wildcards in there. I don't want to use to let use or regular expressions or what have you. I have to concat it with or, again, use the client utils to escape the stuff. Then I need to define a Solr query, tell it to set start and rows. This is basically the pagination information to get the number of total values, so how many documents actually match that result, and then I execute the query again, fetching all those results to really get a list. Otherwise, Solr would kick in and limit my search to 10 results, or the default that is defined within the index. So this is pretty a lot of code. I even added an exception translator and all that stuff that you would have to write not using Spring Data. So what Spring Data in the case of Solr offers you is, again, a query API, so that you don't have to know the syntax, or name, and the or clause and all that stuff, or the circumflex for boosting or what have you, or highlighting. So there is a higher level API, a fluent API, so something we are pretty used to. And we also offer you the derived query mechanism. So this basically boils down to, again, having just that method as within your repository interface. And that's all you need, and you're good to go to execute the search as long as your index matches what you want to do. That's always there. Okay, are we doing time? Have to hurry up a little bit, so I'll skip that one. As we saw boosting before. You can basically define boosting via the circumflex, and in Spring Data Solr it's pretty easy to do query time boosting by just having the add boost annotation on any method parameter you want to have, and we'll make sure that this annotation, this value gets picked up, is applied to the actual query executed, which is a kind of nice thing. And we also have support for the scoring, because again, as in MongoDB, by default, the score is not returned for an individual document. So you have, basically in Solr, if you are interested in the score, you have to define the fields that should be returned as part of the result. And let me just quickly show you that. You basically would have, this is FL, field list. You would have to, as you can see in here, here's the document, and it doesn't have a score field. There is none in there. So you have to define, I want to have all the fields, and I want to have the score field as well. And then execute the query, and all of a sudden the score field is in there. So it's not very useful for that particular query. But if I combine it with some other criteria, the score would change. But the point is, what we have for you is not only that one, but also the other annotation. As we saw in MongoDB, there is text score, and as those two projects evolve on a different pace, in this case, it's just called score. There's something in Elasticsearch as well, and we're trying to move those sometime in the future together to have it unified more or less, so that there is a dedicated meta annotation that indicates, hey, this is relevant for search and it's a score field. So we can do that with the composable annotation model we have in Spring as well. So, but that's something we want to do. Okay. And as you saw before, the result highlighting is you have to know about the HL parameter. You have to know how it's done. And with the Spring Data abstraction, it basically boils down to this very one annotation. So you can add highlight, define a fragmentation size and the number of snippets. So it basically tells you how many characters from beginning to end where the search term is found is returned, and how many snippets in maximum should be returned. There is a bunch of other parameters as well, let me just, there's the highlight, and there's quite a few others as well. So you can define the fields, you can find a format, a prefix, a postfix if you don't like the default. The default is EM, I guess, yeah, and you can define an explicit query. So there's lots of options within that annotation. So it's pretty much everything the Solr API offers for you, and quite simple in there. Okay, and the last thing I wanted to show you is about the Schema API. So what we learned in the beginning is that there is a schema in there, and that Solr tries to guess what it looks like. And what we offer you is basically the @indexed annotation, so that you can give hints to the search server how to treat fields and the types in there, which is kind of handy and hopefully prevents you from running into reindexing issues. So if you want to use it, it's there for you. It uses the Solr 4 Schema API. We recently upgraded master to Solr 5, which is coming with the next release. But yeah, it's there for you to use, and pretty simple. It was just as you expect it to do. The @indexed annotation can be used as an alternative to Solr's very own field annotation, which doesn't allow you to define index informations in there. Just tells you which fields to be indexed, but not how. With this one, you can do it. Okay. Then let's move on to the final part of this talk, which will be about Elasticsearch. We saw a lot of Elasticsearch in the beginning. So it's basically this search server that takes the JSON documents, has this schema detection. It even allows you to have nested documents within your structures, but that can drastically decrease performance if you use it. So be careful with that, especially when doing queries. And what I wanted to show you in Elasticsearch is basically the indexing stuff. So you have the add document annotation that lets you basically define where your domain type should be put. So it is possible to have an index defined via the @index name, which is the root type. And then you can store different types of documents within that collection. So this book is basically stored in the publications collection and is of type book, obviously. So if I translate this to a request to Elasticsearch, it basically is a put on the index publications with type book and some ID, what have you, and the values as part of the JSON document. What I now can also do is have a class article, which is also stored in the collection of publications, but is of type article. So the schema up there would change to publications article, what have you, ID. The thing you have to be aware of is that the properties of both those types need to match. So if you have, let's say, a name in the book type, which is of string, and you have a name in article, which is a name type or value type, what have you, then that's not allowed. This will give you an indexing error. So those have to match. If you have a name in one, you have the same type to have the same in the other. Okay, and Spring Data Elasticsearch also offers you, same as with Solr, some kind of API to influence the structure of your schema. So in Elasticsearch, it's done via the add field annotation that lets you define, basically lets you define the type of the field. So you can have basically a string that is a date and tell Elasticsearch to apply to that specific string to treat it as a date with a specific format. Or you can use geolocation data in there, which is translated to a long lat type and what have you. Interesting is the multi-field annotation, because that one basically creates, you can assign different analyzers and indexes, as we learned today, to a specific field. So it basically, in that case, it would be an authors field, and there would be a dedicated field that's used for sorting using a keyword analyzer, so a different analyzer than the actual one. And so there would be an additional field, authors.sort, using the keyword analyzer. So this is pretty neat because it helps you set up your domain type to be really, really searchable for the use cases you have. Well, so there's of course a dedicated query API that you can use. There's the very own Spring Data criteria API for pretty simple queries. So you basically define where location and use some geo point, and then you're good to go. Of course, there's Elasticsearch has many more capabilities than just doing search by some properties. So you can basically go on and use the native search query builder, it's called in that project, to and then apply filters to it. So you can define a Boolean filter with exactly the same terminology as you have within Elasticsearch in the web UI, as you saw when you construct the command. So it's a Boolean filter with a must, and then the terms must match Spring and what have you. So you have access to all the Elasticsearch capabilities via the native search query builder. Okay, so let me just show you some Elasticsearch. With Elasticsearch, I wanted to basically show you faceting. So this is used for the guided navigation. And as I said before, there is the facet abstraction in there. So as a result of a faceting query, you get a facet page in return, for which you can basically get out the terms. So in this example, there is a list of conferences in years, and the conferences are about a bunch of terms like Spring, Scala, Elasticsearch, Kibana Cloud, and what have you. So this is the content of the conference. And we want to know for all the documents within that collection, basically, how often does the term Java or what have you occur. And when I execute that, it's a regular Spring Boot app. So all of those store implementation basically have Spring Boot auto configuration for you ready. And when I execute the query, you can basically see, oh, my query for all the documents, there are 4 conferences that match Java, 2 for Spring, 1 for Scala, Play, Kibana, Elasticsearch, what have you. So this is pretty nice for the guided navigation and pretty handy. Since Elasticsearch recently, well, it didn't actually remove facets, but it deprecated facets in favor of aggregations. There is support for that as well. So aggregations are the next step of facets, so to speak. They are facets on steroids, so you can do much more. There's dedicated documentation on the Elasticsearch site. But just to show you the very same query in another way using the aggregations is basically I have a search query, the same as before, for a search type, and then I add an aggregation for a terms builder. That's basically just the same as we saw up here, just that it's formatted a little differently, and that I don't use a facet with a facet request builder, but I use the aggregations, and this basically just gives me the same output as before. So there is support for both the old and the new versions of faceting. Okay, great. We saw facets, we saw aggregations. This brings me more or less, hey, we got a few minutes left to the end. All of the code you saw today is available on GitHub. You can check it out, play around with it. There's our very own Spring Data examples Git repository. There is all the examples we have in there for Cassandra, Elasticsearch, JPA, so all the other store modules as well. Everything I showed you today is there, up there. You can check it out, as well as the others. Sometimes we're already crafting new features within the examples, so you may want to check out some of the development branches of those as well to see what we're up to for the next release. But yeah, if you got any questions, feel free to ask or come to the Birds of a Feather. I guess it's tomorrow, or come by later. I'm here for the rest of the conference. If there are no questions, I wish you a very nice rest of the conference. Enjoy it, and goodbye. Thank you.